Welcome to the presentation of life cycle analysis of concrete slabs with various supplementary cementing materials and a literature study on service life, durability aspect, and abiotic depletion potential. The changes in the climate that we observe today are seemingly consequences of long pattern of overconsumption by humans. The substantial reason behind the environmental degradation and the eventual loss of resources, global warming, and pollution is majorly carbon footprint. Carbon footprint is the mark you leave on the environment through every action that releases carbon. The harmful gases such as CO2. The impact on climate change is a result from the carbon emission from anthropogenic activities are one of the major challenges in attaining environmental sustainability. Approximately 40% of annual global greenhouse gases emissions come from buildings, where embodied carbon is responsible for 28% of building sector emissions. Use of cement in concrete plays a vital role in emission from building industry. Cement production currently accounts for about 5 to 7% of global emissions and is also the most crucial ingredient in one of the most common building materials globally. It is unimaginable to think about a world without concrete as we have across the globe. Bridges, offices, houses, dams, power stations, tunnels, and an infinite number of structures that are made with concrete, from the immeasurably massive to the humble stepping stone. The structural engineers who take part in most of the design aspects of buildings can play a significant role in turning the construction into more sustainable and greener ones. With the right choice of building materials and adapting wise strategies during the design phase so that the buildings will have a longer service life and lower emission during their service life. A considerable amount of CO2 is from the heat produced during the non-stop running of hot kilns. However, half of Portland cement's emissions come from calcining limestone, which produces CO2 during the chemical reaction. Therefore, the most effective way to reduce the negative environmental impacts of concrete is to limit the use of cement or replace it with secondary cementitious materials. Building materials with carbon storage potential can offset the emissions from other materials in the buildings to achieve a net zero carbon footprint. The LCA results using one-click LCA of a simple residential building showed that the use of fly ash and slag can reduce the embodied CO2 in concrete considerably while comparing with that of ordinary cement. Since fly ash and slag are industrial byproducts, the use of those supplementary cementing materials corresponds well to this purpose in a way conserving the virgin materials like limestone and silica. The literature study revealed that the use of supplementary cementing materials not only provide the environmental benefits but also make the concrete more durable and improves the service life of concrete structures, especially in harsh environments. The analysis of impact characterization parameter abiotic depletion potential through one-click LCA showed that the abiotic depletion potential will be more in the case of normal concrete as the virgin materials such as lime and silica are required in abundant quantities for cement production, whereas industrial byproducts such as fly ash and slag considerably help in reducing the resource depletion. Thank you very much for your kind attention. Global warming is real, the climate is changing, so should we.